Okay, let's get started then. So we're going to start our first real lecture on machine learning, and we're going to start super simple and gradually make things more complex. So if this seems really simple at the beginning, it should be, but don't worry, it will get more complicated. Okay, so the way that each of these units work is there's going to be some practical data set, some practical problem we're trying to solve with machine learning. And so the lecture slides will include pictures of the code, which is in the form of a Jupyter notebook. And the theoretical ideas will be applied, you'll see them applied to that particular problem. So for this first unit 1, the objective and the data set has to do with predicting automobile miles per gallon from features like number of cylinders in the car, the horsepower, the weight, etc. And there is a demo 1, and you can find that in the main course repository. You can download it, run it, or you can run it in Colab if you'd like to, or if you don't want to run it, you just want to view it, you can do that in an HTML browser once you're logged into GitHub. This particular demo loads data from OpenML, which is a repository of many data sets. And the way that we're formatting, you could say, or loading the data is we're loading it into something called a Pandas data frame. And Pandas is a very popular way to sort of display the data and summarize it as a first step to understanding what you're dealing with in machine learning. And so it's a library of many different commands and objects, and the data itself is loaded into what's called a data frame, a Pandas data frame, and it has 3 main fields. So this is like object-oriented programming, where you have an object like df here, and that object has many things inside it. It has data fields, it has functions, and you access all those things with like df dot, and then either the command or the field. So in this case, the 3 main fields, once you load your data into this data frame called df, are the values and the numerical values of the data. There's going to be column labels and row labels. I'll show you in just a moment. And there's also many other functions and so on. So here is what the Pandas data frame looks like for our data set. And so first of all, you can see there's an array of numbers.
Professor?
Oh, let's see. Sorry, I didn't realize that the screen is not going on. All right. Just try to start again. I don't know. It usually behaves in this room, but I'm not sure what the problem is today. Okay, I think it should be working now. Sorry that I didn't notice that for a while. If you see that ever happen again, just let me know as soon as you can. Okay, so here we are with the Pandas data frame, and you can see that there's an array of numbers, and across the top you have the names of what we call features. These are the things we're using to do our prediction. So in this case, you see that there's the number of cylinders, in the engine, the displacement, the volume of the engine, the horsepower, the weight, and so on. And then if you look down the rows, these are examples. So here we have a particular car that had 8 cylinders, this displacement, and so on. And this is all in the, okay, so what we did, let me back up a second. So one of the first things we do in Python is we need to load our libraries, the libraries that we're going to use. So pandas here is this library we've been talking about. NumPy is the library in Python that we do most of our numerical processing. It's sort of like, yeah, it has most of the basic math functions. And these are going to be abbreviations that we will use when accessing anything in that library. So if there's a function in NumPy you want to use, you do like np dot and then the name of that function. And so here, sklearn is the library in Python that has most of the basic machine learning functions and stuff in it. And so it turns out that we can, in the sort of subdirectory of sklearn called datasets, we can find this fetch openml function, and that is one that we will often use to load load data. And so here we're going to fetch from openml the dataset called AutoMPG, and notice here we're going to import it as a pandas data frame. So the thing that comes out of here is a pandas data frame, and when we look in the data field, we see this. If you just type this thing without any commands, then without anything else, it knows to just print out this summary of the data. And here you can see it's showing the first 5 samples and the last 5 samples. And you can see there's a total of 398. So one thing about Python is Python always starts counting from 0, unlike MATLAB, which starts counting from 1. So here we start with 0. So this is the data we are using for prediction. The thing we are trying to predict is in the target field of this. So we have data target. And although it doesn't say it explicitly, these are miles per gallon numbers. And so you can see for this first automobile, the mile per gallon was 18. Okay, so that's sort of the data we're working with. These are just screenshots of the demo. You can find the full demo, like I said, in the main course repository. And one of the first things we always want to do when we load data is just try to look at it, because often things go wrong, and it's just a really good sanity check to just look at it. You can often, as a human, humans are pretty smart. You can notice things about data. You can notice when there's issues. You can notice certain trends just by looking at things. So we're going to look at just one of these columns. It's going to be the horsepower column. So we're going to end up looking at this versus this. So in other words, how does horsepower predict miles per gallon? So to do that, we can make what's called a scatter plot. A scatter plot, so each one of these dots is one sample from our data set, and we're plotting, sorry, I said horsepower, but it's actually displacement. So we're going to plot the displacement versus the miles per gallon for that data point, and each one of these gives you one of these blue dots. So just a little bit of extra details about how we got this plot. So for this, we're going to use a library called matplotlib. It's a really nice library of plotting functions, and the syntax is almost exactly the same as MATLAB. So if you're familiar with MATLAB plotting, essentially you know how to use this. And we're going to abbreviate the most important part is PLT. And the other thing we're going to do in order to work with matplotlib and a lot of our sklearn, we need to take that pandas data frame, take the numbers in there, and format them as NumPy. So if you remember, NumPy was the main numerical processing library. So here, this is where we extract, we look at our data values, we want to extract one of those columns, the displacement column. So one of the nice things about Pandas is you're not forced to use a number for the column. You can actually use the name of the column. So here we're taking the name displacement as a string, and we're plugging that into here, and it knows to look at the column named displacement. Okay, and we're taking that list of numbers formatted as Pandas, and we're re-instantiating it or casting it as a NumPy array. And NumPy arrays are the main, that's the main variable type that we will use for our numerical processing. So now X is a NumPy array containing the displacement numbers for our data set, and Y is going to be a NumPy array containing the targets. And now we can just use the scatter plot command to make this nice plot, which shows the overall trend between miles per gallon and displacement. And we can decorate the plot with like a Y label and grid and so on, very similar to how you do it in MATLAB. So this is what we have if we do displacement. We can also, this is the same plot, we can also do this with horsepower, we can do this with acceleration. And so if we step back and say our goal is to predict miles per gallon from, let's say, one of these, maybe displacement or horsepower or acceleration, we might wonder like which is the best one and why. So, so let me just take a random name. Let's see, is Ian Gibson here? Okay, so Ian, what do you think? Like if you had to choose one of these three to predict miles per gallon, which one would you choose and why?
I think I would choose horsepower.
Okay, and why did you make that choice?
It looked a little prettier.
Okay, but like what in your mind? I think you're doing other stuff in your mind.
Yeah, it didn't seem as scattered.
Okay.
Around, it seemed more.
Right. So
Central.
So when you said it didn't seem as scattered around
like I can see like a exponential.
Kind of like a model, a trend,
yeah.
right? So you were kind of imposing a trend on the data, which had to be a function. So for any horsepower, there's only one possible miles per gallon that function can take on, right? And then you were looking at how much does the data deviate from that model. And it seems like it deviates less for that, let's say, hypothesized function than it does for something like that. Right, so that's exactly right. Those are good intuitions, and those are all the things we're going to get into, you know, in a lot of detail. But this is just starting at the very beginning, starting with intuition. So that is, in fact, what we want to do. So now, of course, you know, there's many models we could choose, and we could try to do something very complex or not. And as we go through the course, we will get more complex. But for now, we're going to start with the simplest possible model, the most convenient, mathematically simple model that's possible, which is going to be a linear model. Okay, before we get into the details of a linear model, let's establish some terminology and some mathematical notation. And this is going to be stuff we use all throughout the semester. So you'll get used to these variable names and so on. So to start, the variable we're trying to predict, we're always going to call that y. So in this case, miles per gallon, that's going to be called y. The thing we're using to do the prediction, we're going to call that x. And there's particular names that you find in the literature and textbooks and papers and blogs and so on for these x and y quantities. And I'm listing a whole bunch of them here because in some sense it's important to at least be familiar with all of them, because otherwise when you're reading something, you just have no idea what they're talking about. Even though you understand it, it's just they're speaking a different language almost, right? For this course, when we talk about the thing we're trying to predict, I'm often going to refer to it, most often, as a target or sometimes a label. But I would say probably for now, a target. But it's important to know that other people, like statisticians, might use other names like the regressand or the response variable or the dependent variable, which are, I don't know, a little bit strange if you haven't, you know, taken stats courses, but it's at least a little bit important just to know that these names are out there in case you run into them. And the one that I'm going to use for the thing we're using for prediction is going to be feature. So I will typically refer to the x as the feature, y as the target. So one thing is that in this very first unit, we're starting as simple as possible. And so we're going to use only one quantity for prediction. In the next unit, we're going to be more complicated. And we are going to, for example, use all these quantities for predicting this single miles per gallon. But for now, this unit, super simple. I'm going to use one. So I might use horsepower, I might use displacement, but just one at a time. Okay, so that means that for now, y is a scalar and x is a scalar. And so now that we have those scalar x and y, we can draw these nice plots where we have along the horizontal axis, we have x, and along the vertical axis, we have y. Right? Okay. So the other thing we work with in machine learning in particular is data. And so for these sorts of problems, we're going to assume that we have many examples of x-y pairs, which are those dots on this scatter plot. And we are always going to use the subscript I to index through our data set. And we're always going to use the little n variable to say how many samples we have in our data set. Okay, so xi comma yi, that's a pair that defines one of these dots. And in total, there's going to be n of these dots. So those pairs are going to be called samples. So we have n samples in our data set. Okay, and then this thing on the right is our scatter plot. Okay, any questions so far? Okay, great. So now we can come back to this idea of a linear model, and we need to write this mathematically. So when we talk about a linear model, essentially what we mean is that there's some sort of, the model is a line, essentially. And if you think about a line, it's parameterized by two things: the slope of the line and the shift up and down. And we can talk about the shift up and down as where it crosses the y-axis, which is called the intercept, right? So the slope and the intercept tell us everything about that line. So we're going to use the variable beta 1 for the slope and beta 0 for the intercept. And if y is, the horizontal axis here, y is the vertical axis, x is the horizontal axis, how can I write an equation then involving beta 0, beta 1, and x? So let me call in someone random. So let's see, is Aiden short here? Okay, so Aiden, how could we write y in terms of beta 1, beta 0, and x? Yeah, very good. We'll just write beta 0 plus beta 1x. Okay, so that is going to be our linear model. Now, want to point out one important thing, is that on the left, notice there's an approximation. So this is saying that our data is approximately linear. We're not saying our data is exactly linear because we are acknowledging the fact that our data doesn't fall exactly on that line. However, we do need a name for the thing which is the line, which is our prediction. And we're going to use a y hat for that. So for us, the hat throughout this course means this is like our estimate, our prediction of some true value y. Okay. So, and then one other piece of notation, this triangle equal is a definition. Okay. So, a definition is just basically saying, I'm going to take this and I'm just going to give it the name y hat. So it's not something you can argue with because it's just a choice I'm making. Whereas an equality is really something we should pay attention to. Is we're actually making like some non-trivial claim when we write an equality. When we write a definition, we're just giving something a name. Okay, so that's the difference. So we have here approximation, and here we have a definition. And so basically, y hat is this thing, this is y hat is going to be some function of x, and that is going to be the red line. Okay, everybody with me so far? Okay, and we have, so this model is determined by these two parameters, and rather than writing them as separate things, it's mathematically convenient to put them together into one quantity, which is going to be a vector, and it's going to be this vector beta. And so similar to the homework 0, if you started it, throughout this course, I'm always going to use boldface quantities for vectors. And so here you can see that beta is bold, whereas these scalars are not bold. And that's really useful because sometimes when you look at something, it really helps to know what is a scalar, what is a matrix, what is a vector. And so basically lowercase bold is always going to be a vector for me, and it's always going to be a column vector. So another way to write this is beta. And if I have to write something by hand, it's hard to do the boldface, so I'm going to write an underline under it. But so what we're saying is beta is this column vector. And the reason why I want it always to be a column vector is so that you don't have to wonder whether it's a column or row vector. You just know it's a column vector. Now, if you take that column vector and you put a transpose on it, then that means it becomes a row. Similarly here, because it takes more space for me to put this in the slide, I actually started with a row and I transposed it into a column. Okay? So here we have a column vector that contains our two numbers, and now the parameters of our model are summarized by this beta vector. Okay, and that's going to help us with mathematical notation, with derivations and stuff later. So that's, we're going to start to see more and more linear algebra as this course goes on. Okay, so any questions so far? Okay, so so this linear model is pretty crude. Sometimes it works well, sometimes it doesn't work well at all. But the reason we're using it is just because it's easy. It's easy to interpret, it's easy to analyze, it's easy to optimize its parameters. And so we're just using this as an initial thing. And so, one question we might have that we talked about a little bit before I want to ask the question is, when is this a good model? And I think we have the right intuition that it's a good model when the data is pretty close to that line. And if the data was all over the place here, then maybe it's not such a good model. We will get into very specific ways of quantifying the goodness. And we'll talk about that towards the end of this unit. But for now, the intuition is that we hope that the data approximately follows a line, and then we can feel pretty good about this linear model. Okay, so now the next question is, well, we have this model, it's linear. We know it's parameterized by a slope and an intercept. So how exactly do I choose that slope and intercept to best fit the data? That's essentially the machine learning part. We're trying to learn those parameters based on our training data, the data we have been given. And so again, as I mentioned before, we want to emphasize that the data is not really linear. It's just a model that we're putting on the data. So we have this approximation here. It's not an equality. On the other hand, it's kind of hard to work with approximations because you don't really know what they mean. So it's more of like an intuitive statement more than a precise statement. So let's write it more precisely. Let's say that y exactly equals our prediction here. Let me make sure I get the sign right. Plus epsilon. So epsilon is going to be the error of the model, or the residual, the part that is not, the part of the model that is, the part that's left out of the model that you need to really equal y. So now we have an equality here because we have explicitly included the difference between the model and the data. So So how do we visualize that residual? Let me ask, is Siyu Huang here? Okay, so how can I visualize that epsilon on this plot here? What is that? Where is the epsilon on the plot? So I didn't hear you exactly, but I think maybe what you said was that it's the difference between the sample and the prediction line, right? That is exactly the epsilon. So maybe we'll put that in. So epsilon, if this is the ith data sample, xi, yi, is that blue dot, and then that means that this would be xi, how far we are along the horizontal axis, and this is yi, how far along we are on the vertical axis, and then particular this height here would be y hat I, right? It's the prediction we're making from this, and the difference between these quantities here, that's the error. Okay, so we have the model, which is this nice line here. We have the data, which is this messy blue stuff, and the difference between them are these residuals. Okay, so here's the residual is yi minus our prediction. Okay, everybody good with that? All right. Residual is the vertical deviation from y to the regression line. Okay, so now that we have the errors, we can get specific in terms of how we want to design the parameters. So what we're going to say is we want to choose those parameters, the beta 0, beta 1, slope intercept, so that the sum squared residual is as small as possible. So we write that like this. We sum over our data, I going from 1 to n, the residual I squared. We could also plug in our expression for the residual, yi minus y hat, quantity squared. And notice that these yi's, these are functions, or this is a function of the parameters beta 0 and beta 1, right? So because of that dependence, this overall thing, RSS, we're going to call it, residual sum of squares, this is dependent on beta 0 and beta 1. Okay. So let's go back to the previous picture. And so what we're saying is we will look at all these differences, and we will square each one and sum them all up, and we want that to be as small as possible. So imagine that I made my line like this. Now you can see my errors got a lot bigger, and when I square them, it's bigger. So I want to sort of shift and tilt that line until the sum of the squared errors is as small as possible. And that's just one way of doing it. That's not the only way of doing it. It turns out that this is the easiest one to analyze. But is the idea kind of clear, how we're coming up with our criteria for how beta 0, beta 1 should be set? Okay, so there's other names for this thing. We're going to call it RSS. Some people call it sum of squared errors or sum of squared residuals. But we're going to just call it RSS throughout the course. And maybe you've seen this before. It's kind of a common thing. We're essentially doing least squares fitting. We're saying minimize the sum squared error. That's essentially least squares. Minimize the sum of squared residuals or distances to the regression line. Okay. So can anybody think, just for context, can anybody think of a different criteria that we maybe could use instead of this? And just an alternate? Anybody have any ideas?
Could we kind of change it? Because right now this is almost like the or I guess like the Euclidean norm, could you also do, I guess, like the longest first norms, like just the longest actual error?
Yeah, exactly. We will talk about the different norms, L1, L2 later, but so what you're actually proposing is to replace the square with an absolute value. So in that case, you're using those residuals, but instead of squaring them, you're just taking the absolute value. And it turns out that if you do that, that's actually going to be more robust to outliers in your data. And so when you have these weird points that, like we actually had some here, like this point is kind of far from the trend. And so this guy, when you square that, that's a really big number. So that's going to throw things off. And so if you want a model that's more robust to these outliers, you're actually better off using absolute values. But unfortunately, the math with absolute values is way harder. You can't really derive things by hand. So we can't do that. It's good to know about it, but in this unit, we're going to focus on squares because that ends up being the most analytically convenient thing. It's also probably the most popular in terms of what people do. But it's good to know that there's other options here. Okay, any other questions before we move on? Okay, so stepping back for a moment, what we're doing here is just one example of a sort of a general recipe that we're going to apply to a lot of machine learning problems. And there's essentially like 4 steps. We're going to assume a model with some parameters. So for this first try, we're doing a linear model, and the parameters are beta 0, beta 1. We're going to get a bunch of training data. For us, these are these XY pairs, and we have n of those. We're going to choose a loss function, which is the criteria that we want goodness in. In this case, it's the sum squared error between the true target and our predicted target. And finally, the last part, which we haven't gotten to quite yet, is we want to find the parameters, in this case, beta 1, beta 0, that minimize our loss. So we now have an expression for this. We want to find those parameters, so now this becomes a math problem, something we can just attack as a math problem. Okay, so this is an approach that essentially you do for all machine learning. What differs is your model, your data, maybe the form of the data, whether those are vectors or scalars, and the form of your loss function, and at the end of the day, how you do the optimization is going to be a function of all that other stuff. Okay, so we're going to get into this as we go through the course, many different versions of all this stuff, but this is something we'll see over and over again. All right, any questions? Okay, so so it turns out that what we're going to see is that if we look at the data in the right way, we can summarize the data into just a few numbers, and from just those few numbers, we can figure out, in this case, exactly what beta 0 and beta 1 should be. And when you summarize data, that's essentially the definition of statistics. Statistics are just summaries of data, so you don't have to deal with the massive data. You just squeeze it down to a few important numbers, and you focus on those. And so what we're going to do is we're going to start to think about a few very basic statistics, and then we'll show how those statistics directly can be used to compute the optimal parameters, optimal in the sense of minimizing this RSS. And the other reason we do this is because there's a lot of intuition that you can get from these statistics. They can help you understand things quite a bit. So just probably the simplest, most commonly used statistic is known as the sample mean. So I know you guys have all seen this. So if I have a set of xi quantities, let's see, I'll ask, does anybody know, let's see, is Kiernan Cagle here? Okay, so how would we write the sample mean if we have a bunch of xi's? And let's say I have a total of n of them.
Wouldn't it just be 1 over n times the summation of from I to I equals 1 to n?
Exactly. So that's the sample mean. And it's really just, it's just the arithmetic mean of this list of numbers. There's nothing really complicated going on. There's no random variables. This is not expectation, if you're familiar with that. This is not a statistical mean, this is a sample mean. This is just someone gives you a list of numbers, you sum them up, you divide by the number of terms in the list. And we're going to give this the name of this thing when we do it with the x variables, we're going to call it x bar. We can do the same thing with the y variables, which are the targets, the things we're trying to predict. And we have n of those, so the sample mean y bar will be 1 over n times the sum of the yi's, where I goes from 1 to n. So intuitively, that tells us the average value in the x's and the average value in the y's. Now, the next most important thing to know, once you know the average, is you want to know, well, how much does it spread around that average? And so the most common way of looking at that is to look at the variance. And in particular, we're looking at just from this list of numbers, how can we define the deviation from that mean? So we're going to have xi minus the sample mean. So that deviation, we're going to square it. We're going to sum over that, and we're going to average 1 over n in front of that. So that is going to be the sample variance. Okay. We can do that with x's, and we can do that with the y's. So 1 over n times the sum of the quantity yi minus y bar squared. And this picture can give us a little bit of intuition. So what we're showing here is a histogram. We have 2 data sets. We have like a red data set and a blue one. And when we look at this red data set and we're asking, so essentially what we're seeing here is there's the data has been binned here, and we're showing how many samples are in each bin. And based on this histogram, you might ask, you know, what's the mean of this? The mean is somewhere in the middle. It's basically, it's where the middle of the histogram is. And the variance tells you the width around the mean. Okay. But the one important thing about the variance is a squared quantity, whereas the mean is, you know, not squared. So in some sense, they're like different units altogether. So maybe if this is, you know, miles per gallon, the units of this would be miles per gallon squared. So you have to be aware of that. So because there's that mismatch, miles per gallon, miles per gallon squared, sometimes it's more interpretable to get rid of this square, in which case the sample variance, once you take the square root of it, becomes the standard deviation. Okay, so the standard deviation, in particular the sample standard deviation, is just the square root of the sample variance. And the nice thing about that is that has the same units as the data itself. So now, if you want to know what the sample standard deviation is, that is directly proportional to the difference between the center of the data and how much it spreads around that center. Okay. So that would be, in this notation, it would be like Sx or Sy, because we're just removing this square term. Okay, any questions on this? All right, so a lot of times someone will ask at this point, why are we using 1 over n here? Because sometimes you'll see other sources use 1 over n minus 1. And that's a great question. We're going to get back to that and answer that very precisely in a couple units. It has to do with something called bias. We're not really ready to talk about that yet. So I'm just going to note that for the purposes of this unit, we definitely want to use 1 over n. We do not want to use 1 over n minus 1. If we use 1 over n minus 1, all the other equations we derive would be, let's say they would be way more messy. When we use 1 over n, all the equations are super nice and clean. So 1 over n is the right thing to do for us right now. And we will talk about the difference between 1 over n and 1 over n minus 1 later. It's something you have to be a bit careful with computationally, because sometimes, depending on which software package you're using, it may default to this or it may default to this. You kind of have to read the details. So because you have to read the details, sometimes it's not so convenient to go have to look up the documentation. It actually might be simpler to implement this directly, as I'll show you in a couple pages, where you don't have to guess as to what this software package, how it defined variance. Okay, so here we are back to our scatter plot. We have horsepower on the horizontal axis, miles per gallon here. Again, this is like Y and X. So if we had to just visually guess what is X bar, let me see. So is Vasilios Konstantakos here? All right, so what do you think if you had to guess just visually, what would X bar be?
Probably around 100.
Okay, yeah, something like maybe like this. And so I think, to do that, you're sort of just looking almost like where would this thing balance on the horizontal axis, and then maybe for Y bar, maybe it would be roughly there, maybe a little bit lower, somewhere like that. And then what about the standard deviation? So let me see, is Blake Morse here? No? Okay, what about Lokesh Nanthakumar? No? Okay. Oh, you're here. Okay, way in the back. All right, so what would you guess that the standard deviation is for X? Okay, it's basically just like some spread, like, would a value of 100, let me ask you this, would a value of 1,000 be reasonable? No, right? Or would a value of 1 be reasonable? Probably not, right? So it's something maybe, something like in this, we won't know until we actually compute it, but the idea is just, kind of visually, intuitively, it's some measure of the spread. It should be not like the extreme, but somewhere in the middle. Okay, so that's what we have. Now we can do this using the NumPy package in Python. In particular, it has a mean function, so to access that you do np, because we abbreviated that package as np, so you do np.mean, apply that to x. We're going to assign that xm, the variable, and when we look at the value, it's 104.47, which is not far from our guess of 105 or 100, I think it was. And can do that also for y. The mean of y is 23, which is around here. And when we do this to compute the variances, like I said before, we could use np.var, but then I'm not sure exactly what normalization that uses. So instead of doing that, to be safer, I computed the variance based on the definition and the mean function. So what I do here is I look at the difference between x and its mean. This double asterisk is squaring element-wise. So x is a vector, xm is a vector. Subtracting it, you get this vector of differences. You element-wise square them. You have a new vector, and then I can take the mean of that, and according to how we define the variance, that's what this is. And now to get the standard deviation, we can take the square root, and we have that's about 40 in the x, so that's like about this much or so in the x domain, and 7.8 in the y domain, so that's like something like this in the y domain. Well, actually, maybe a little bit bigger. Okay, so those are just to get the intuition. Any questions on these? Okay, so so these statistics are the most basic ones, but if I'm predicting y from x, I can't just talk about x on its own and y on its own, right? I need to know how they relate to each other. And so the most basic statistic about how two random variables relate, or two let's say, data sets relate, is the sample covariance. So let's see. I don't know if you guys remember how this is defined, but basically, in spirit, it's a lot like the variance, but with two variables. So it looks like this. You have xi minus its average. And then rather than squaring it, you take yi minus its average, and then you take the average of that quantity over the data. Okay, so this is one way to quantify how related these two variables are. Now the thing about this, it's a little bit confusing, is that this particular definition responds not only to how related they are, but how large x is and how large y is on their own. So if I take x and y and I double both of them, then you can see that this would increase by a factor of 4, which doesn't mean that they're more related, they're just bigger. So to get rid of that scaling kind of confusing part, it's typical to normalize this sample covariance. And the way that you can do that is you can take SXY as defined above and divide by the standard deviation of x and the standard deviation of y. And now, if you double x, what happens is that the numerator will double, but the denominator will also double. So now it's invariant to the scaling of x. Similarly, it's invariant to the scaling of y, so it's a lot more interpretable. And in fact, this number is always going to be in the interval between 1 and -1. Okay, so this is interval notation, closed interval, meaning it can be exactly -1 or 1 or anything in between, but it can never be outside that. And let me give you some pictures of scatter plots. So when you have a scatter plot like this, if those points are perfectly on a line, that means the data is perfectly correlated, and this rho xy would give you a value of 1 if all the points were perfectly on a line. As those points start to deviate from the line a bit like this correlation, this normalized correlation, starts shrinking towards 0. As it gets fatter and fatter, eventually, when you get to 0, there's no particular trend. It's not really on any line at all. It's just kind of this circular cloud. Then, as you get closer and closer to a line with negative slope, this correlation coefficient gets closer and closer to -1. Okay, so here you can kind of see a range of values. And especially when we're talking about linear prediction, linear regression, you can see this is very important, right? Because we said we wanted our data ideally to be on a line. So in some sense, that says, like, ideally, we want this sample correlation coefficient to be 1. Now, in reality, it's never going to be 1, but we'll see that ends up giving us a particular way of understanding how well we can predict a particular data set by looking at that particular statistic. Okay. Any questions on anything here? All right, great. So we're almost done. So the last thing is that when you're doing derivations, particular quantities often come up, and it's good if you can relate those quantities directly to the sample mean and sample standard deviation. And so I'll show you a trick here, which is an alternative expression. And we're going to start with the definition of sample variance that we saw before. And let's expand what we see here. So if you look at this quadratic term, how can we expand that into 3 numbers? Let me ask, let's see, is Sri Tirumala Raju here? Okay, also in the back. All right, so how can I expand that quadratic into 3 numbers? A sum of 3 numbers. Okay, so it's just simple algebra. So we get xi squared minus 2 xi bar xi plus x bar squared. Right? I'm just taking the quantity xi minus x bar squared, and I'm multiplying that by itself, collecting terms, and this is what we get. So now let's go one step further, And we have here essentially like an averaging operation. This averages across the I variable. So this averaging operation is linear. If I average the sum of these things, I can also say I'm going to average the first, and I'm going to add that to averaging the second, and I'm going to add that to averaging the third, right? Because addition is distributive. So essentially, here I'm writing out. So the first term is the average of the xi squareds. Now let's look at this term. If I take the average of these, because the x bar doesn't have an I index on it, I can actually move it out of the average and write it on the left side, right? So do you see how that second term became this? Any question on that? Okay, and similarly, if I average this constant that has no I dependence, it's like I'm seeing x squared over and over again. It's all the same. I average, I just get the x bar squared, right? So that's where I get this. Okay. Any questions on this? Okay, can we simplify this at all? Let me see. So is Gabe McGinn here? No Gabe? Okay, what about Yashvi Malhotra? Okay, so how can we simplify?
So first term, I think we can use.
Let's leave the first term. Let's focus on the second term actually.
So the second term would become 2x squared.
Exactly. So we can remember that this is actually the definition of x bar, and then we have minus 2x bar squared plus x bar squared. And so we can combine those last two terms. So we have this minus x bar squared. And now from this last expression, we can rearrange the terms, and we can write on the left side this summation. This is something that often comes up in derivations, the average of the squared, xi squared. And what we're seeing here is that this equals the variance plus the squared mean. Okay, so this is a very useful thing because this is something that often comes up, and now you want to write it statistically. It is the variance plus the squared mean. Okay. Sometimes students confuse this for the variance, but actually you have to remember that there's this squared mean in there as well. Okay. Any questions on this? Okay, we'll use this a little bit later in the next lecture. So we can also do the same thing for this expression for the sample covariance. Essentially, we follow the same steps. We write this as we have an xi, yi term. We're going to have a x bar, y bar term, and we're going to have two different cross terms, this one and this one. And essentially what we will get at the end of the day is we're going to get 1 over n times the sum of xi, yi minus x bar, y bar, because of certain terms canceling. And now if we rearrange this, we get this useful expression that if you ever encounter the average of the xi, yi product, that you know that this is the sample covariance plus the product of the two means. Okay, so this is another term that often shows up in derivations, and we can easily simplify it as that. Okay, any questions on this? Okay, great. So, so basically that's almost it for today. I just wanted to sort of summarize these simple statistics that we just discussed. So we have the sample mean, call that x bar, here's the formula. And when we write our code, we'll try to call that xm. We have the sample variance. We can write it two ways. We can write it sx squared. But if you remember how this sample covariance was defined, and if you use, in place of this yi minus y bar, you use xi minus x bar, then you get exactly this, right? So that suggests an alternate way of writing it as sxx. Okay, so either one works. And then we have the sample standard deviation. That's nothing more than the square root of this quantity, or the square root of that s double x. And similarly, we have our sample covariance, and the sample correlation coefficient was this normalized version. So, so that's it for today. Next time, we'll dig deeper into how we optimize the beta 0 and beta 1. If you guys have any questions, feel free to come up, ask me now. Have a good one.